ever wondered how this periodic change in oscillatory motion happens? We hope your curiosity will be fulfilled by the end of this video. Let's come to a simpler case. Let's look at the components of a coupled pendulum. This is a stand, and here we have one simple pendulum with a bob at its end, and we also have another simple pendulum with a similar bob. Other end of both pendulums are attached to a coupled medium, which is a thread in our case. Let's look at it in action. Now let's understand why this is happening.
As we have seen the components of the coupled pendulum, let's see the working principle too. Let's take a case where one of the pendulum is set into oscillation and the other remains stationary. In this case, as both of them are suspended, the one that is remaining stationary tries to stop the oscillating one. As a result of which, the oscillating one comes to a halt and the one that was remaining stationary will start oscillating. From this pattern, we get to know that there is an energy transfer between both the pendulums. The energy transfer is happening via the medium that is connecting the pendulum. As we have seen here, the motion of one of the pendulums is obviously affecting the motion of others. Hence, we say that both of the pendulums are coupled to one another. They can be strongly coupled or weakly coupled depending upon the medium by which both of them are connected. If the medium is a rigid one, then the coupling effect is negligible. But if the medium is a soft one, like a thread we have shown, then the coupling effect is very much negligible. The most important parameter which decides the nature of motion of the pendulums is the phase angle, which is the angle made between both the pendulums. Depending on different phase angles, we have three most important cases. One is where both of the pendulums are starting the oscillation from the same position, which is where the phase angle is 0. The second case can be where one of the pendulums is at the mean position and the another is making an angle with the mean. The third case can be where both of the pendulums are making an angle with the mean position and they are at opposite sides of the mean.
Let's look at the mathematical modeling of coupled pendulum. Coming to the force equations for the system, the force on pendulum A is given by minus KL into theta A minus theta B, whereas for pendulum B it is minus KL into theta B minus theta A. Hence, the equations for motion turns out to be second order differential equations, where theta A and theta B are the angular displacements of the pendulums, K is the force constant and M is the mass of the bobs. Normal modes are the conditions where the system oscillates with same frequency and pass through the equilibrium position at the same time. Here, mode 1 is taken to be symmetric, where both the pendulums have same amplitude and same phase. Then their angular frequency omega 1 is given by omega 1 square is equal to G by L. Mode 2 is taken to be antisymmetric, where both the pendulums are having same amplitude but opposite phases. Then their angular frequency omega 2 is given by omega 2 square is equal to G by L plus 2K by M. Beats are the most interesting aspect of coupled pendulum. This happens when energy transfer occurs in back and forth direction between the two pendulums when initial conditions are chosen appropriately. Beat frequency omega b is given by omega 2 minus omega 1 upon 2 and average angular frequency is given by omega 2 plus omega 1 upon 2. For weak coupling, the beat frequency is much less than the average angular frequency. Hence, for theta A, the terms inside the square bracket change much slowly as compared to the terms outside it. This creates a phase difference, and hence when one of the pendulum is at rest, the other moves with maximum amplitude.
Here the phase angle is 0 and the pendulums make a non-zero angle with the mean position. We take this case as mod 1, which is symmetric. Here the phase angle is non-zero and both the pendulums make an equal angle with the mean position. This is the mod 2 in our case and it is antisymmetric. Here the phase angle is non-zero, but only one of the pendulums make a non-zero angle with the mean position. We take this case as mod 3. I hope you got the answer for the question we started with. Next time you see such an oscillation, you know that it's because of the coupling effect and energy transfer. It's not a perpetual motion. It will for sure come to a halt.